Hi everybody, today we're doing a mechanics paper from A2 Maths. So first question, this is asking us to work out a little bit of a differential equation about a particle moving in a straight line. So nothing too difficult. So we have our particle P moving along, and we're given that it passes by this point O, say an origin. At some later time, say time t, its velocity is v. So the velocity is a function of time, right? Initially, so let's say that v is v of t, and we know that v at time naught, that's why I'm decided that t equals 0 when it passes O. V at 0, which is also called v naught, is 2 meters per second. So we're told that the acceleration is this here. Well, what is the acceleration? It's just dv dt, right? So dv dt is equal to e to the minus v over 2. And this is a simple differential equation for which we use separation of variables. So we take the dt over there, we take this thing underneath the dv, so we're putting all the v on the left-hand side and all the t on the right-hand side. So if we take this, it's e to the negative, and we divide on both sides by it, we sort of get e to the positive on this side. So we have e to the v over t over 2 dv is equal to dt. And now we're going to integrate this. So what are our limits? So we want to know the velocity at time t is equal to 1.2, and we already have the information about the lower limit, which is t equals 0. So we're integrating the time from 0 to 1.2. And we know that the velocity at time 0 was 2, and we're looking for some v here, some v prime. So these are pretty easy things to integrate. So we get 2 e to the v over 2 from 2 to v prime. That's just the way you integrate a exponential. And we have this is equal to, well, this is just integral of 1, which gives us t, evaluated between 0 and 1.2. And now just something that's worth mentioning, if just in case occasionally falls out of your mind. Oftentimes we get a 0 in the lower limit, and we're used to kind of ignoring the lower limit. So for instance, this thing on the right-hand side will just be 1.2 seconds, right? Because the lower limit, it's 1.2 minus 0. That's not the case here. So you must remember to look at both limits, just in case that is something that you might forget. And even if the lower limit was 0 here, even if that was true, this would be e to the 0, which is not 0, it's 1. So just be a little bit careful. Otherwise, it's just e to the v prime over 2 minus e to the 2 over 2, which is just 1. And I think you can get the rest from that. So you're going to have to take the natural log of both sides, and so on. So you should end up with an expression like v as a function of time is 2 natural log of 1/2 t plus e. Hope you're happy with that. Okay, question 2. So we've got this very complicated looking system, and they've given us a whole paragraph about all the stuff that's going on. So the first question, which is here, show that the tension in the string is 20 sine theta. Well, here we have this, the tension in the string is here. And we know that this is a uniform rigid rod, and this is a light elastic string. So we know from our formula booklets that if there is an elastic string that's been stretched, the tension in it is lambda over L times x, where lambda is the modulus of elasticity, L is the natural length, and x is the amount that it's been stretched by. So what's the situation here? Well, we are told the modulus of elasticity, and we want to know, and we know the natural length. So what we're looking for is x. So that's going to be 0.8 meters. So it's already been stretched 0.8 meters here. So it's whatever length this side is, that is the amount it's been stretched, because it's already used up all this natural length going up to the pulley, and then there's another bit here. So this is a right angle triangle. Well, what's the length of this side? This is just a right angle triangle, you know theta, so this has got to be 0.8 sine of theta. And that's just the amount that it's stretched. So what we have is, for the first question, so I'll put question 1 here, because it's easier to see. So we have that the tension is lambda, which is 20, times 0.8 sine of theta, divided by 0.8. So it's cancel, and you get your solution. Okay, so the next one is more like a little mini written question. It's only worth 1 mark, so you don't have to say too much. And you say, explain why the part of the string attached to the ring is perpendicular to the rod. So that was something we used here, right? Now, the reason we could use that fact, it's perpendicular, if it's a right angle, that we could get, that was how what we needed to get the previous answer. It comes from the fact that this is a frictionless rod. So it's a smooth ring, basically, or it's a frictionless ring. So it slides up and down the rod without any friction. Now, if this wasn't perpendicular, if there was any deviation, so say it was coming in at like a really sharp angle, or coming in at a really broad angle, then, or either way around, then this would cause unbalanced forces, and so the ring would move. Now, the only way you could have this is if there was friction to combat those unbalanced forces and actually keep it at this artificial angle. But there is no friction, so it will just settle into its equilibrium position, which is this. So pretty much all you need to say is that the fact that it's a smooth ring. Okay, so now they're asking you to find theta. So to do this, you're going to be using moments about A, and you're using the fact that it's in equilibrium. So let's do that. Moments about A. And you know that if it's in equilibrium, then the moments must be balanced. If there was like a net moment, then it would rotate around A. So we want to be resolving these along the axes given where one is the rod and one is perpendicular to the rod, because this always makes it easier for us. And we only care about the moments are only comprised of forces which are acting perpendicular. Anything that's acting along the rod doesn't exert a moment on a point. So what forces do we have acting? Well, we have this this thing here acting that far away. We also have the weight of the rod, and we have the weight of the particle. So we could faff around here with working out the center of mass of the rod particle system and doing it from there, but actually you can just do them individually. So let's first work out what this distance is here between the axis and the ring. Well, that's pretty easy for us. This is just 0.8 cosine of theta. And now the center of mass of the rod just on its own is obviously half of 1.2. So this one, we can do that. Okay, so let's have moments about A. So we've got some of this string acting on the giving a moment, but it is completely perpendicular, and that is the tension. And it's 0.8 cosine theta away from the axis. And by the way, I apologize for my voice. I just got a bit of a cold, but it's nothing to worry about. So we have the tension times 0.8 cosine theta. So that's acting kind of in that direction. Now we've got the weight of the rod. So the perpendicular component is mass of the rod times g, and then we'll work out that theta is also this angle. So if we do it, so that's theta, therefore this is 90 minus theta, therefore that is theta again, therefore that is 90 minus theta, therefore, oops, that is theta. That's the right angle. So this is mg sine theta. And at the end of the rod, we also have pretty much exactly the same thing, the mass of the ball sine theta. So we have t times 0.8 cosine theta minus, because both of these are acting downwards, mass of the rod, g sine theta, times the distance, which is 0.6, minus the mass of the ball, g sine theta, should be a g there, times the distance the ball is away, which is 1.2, and this is all equal to 0. So if you solve this, you know that t is, we've already worked it out, it's equal to 20 sine theta. So you're going to get a sine theta in every one of these terms, so you can cancel it all out. So this is going to be 20 times 0.8 times the cosine of theta minus mrg minus mbg. And that's pretty easy to solve for the cosine of theta, and therefore for theta. Okay. So question 3. So again, it's kind of differential equation-y kind of stuff, but very similar. So we have a particle P, it's moving on a smooth horizontal surface and passes some fixed point O, which we're going to call our time is equal to 0 point. So let me draw that again. Point O, t is equal to 0. And this is now at some later time t. And the velocity here is 8. Velocity here is v of t. And it's moving against this, so it's moving on a smooth surface, so there's no friction to think of, but there is some force acting on P in the direction from P to O. So it's acting against, again, towards the origin, like it's what we call a restoring force. So the force that's acting, which of course is equal to the mass times the acceleration, is equal to minus 2x. So it says magnitude 2x, but we put the minus in to account for the fact that it's in the opposite direction of x, where x is like the amount that we've moved, and x sort of runs that way, you know. So here x was 0, and here it's, you know, some number, and it's increasing, it's all positive. So therefore the force, which is acting in the opposite direction, must have the opposite. In fact, these things are all vectors, really, which might give you more of an idea of what's going on here. This vector is acting in the opposite direction to what that vector, because that vector points from there to there. I hope that's clear. So we have this equation. Well, we know that dv dt is just the acceleration, so that's equal to minus 2 over m x. And then we use the chain rule to express this as dv dt dt dx. Wait, what? No, sorry. dv dx dx dt. Well, dx dt is just v, so this is equal to v dv dx, which is minus 2 over mx, as we had before. So this is our k, minus 2 over m. Now, question 2 is the integration part. So we have this this differential equation, and again we're going to do just simple separation of variables. Take all the v's on the one side, all the x's on the other, and then integrate both sides. So we've got v dv is equal to minus 2 over m x dx. And we're integrating this between some time where the velocity is at the beginning, we're past O, so that's where the velocity was 8. And at that, these limits have to match, right? So when the velocity was 8, x, the displacement from the origin, was 0. And now we're looking at some final time where the velocity is 0. And we want to find out, we're just going to put x here because we want to find out what that number is. So x prime. So we have 1/2 v squared between 8 and 0 is equal to minus 2 over m 1/2 x squared between x prime and 0. So we have that minus 4 is equal to minus 2 over m, sorry, not minus 4, minus 32, or whatever. There's a half on each side, so I can actually get rid of that. So minus 64 is equal to minus 2 over m x prime squared, blah, blah, blah. You can get x prime. Excuse me. My goodness. Okay. And that's all you need to do. So again, separation of variables, and just make sure that the limits match, and you're just careful when evaluating it. And you get the answer. Okay. Question 4. So this one's about rotational motion. So we have a light, inextensible string. That's that guy. So because it's light and inextensible, it means that the tension is the same everywhere in the string. So that tension is the same as that tension. And that's important because the first question is asking you, calculate the speed of B. So to know the speed, we need to know from the equation that F, the sort of centripetal force, is equal to mv squared over r, which is also equal to m r omega squared, because omega is r omega is equal to v. So this is going to be the force that's acting towards the center, the one that's sort of pulling B around, really. And that's what we want to know. So we want to know what the hypotenuse of these triangles are. So now we can look at the balancing of forces for this particle in the vertical direction first. So we know that there is mg pulling down. We know that there is t cosine of 30 pulling up. And also there is t cosine of 45 pulling down. And we know that the ball is not moving up and down, therefore these forces must all balance. So pulling up, we have t cosine of 30 minus mg minus t cosine of 45 is equal to 0. And then you can solve for t, because a t is equal to mg over the cosine of 30 minus the cosine of 45. And this will give you an expression for t. So we have t now. It's in fact 6 over square root 3 plus square root 2. So now we are looking at this equation. And remember, we're looking for the speed of B. So that's going to be this V in the equation. And we know that the force pulling in is the force of the tension in this string and this string, the horizontal components. So there's two parts of it. There is t sine 30 and t sine 45. And that's equal to mv squared over r. Well, we found t. We know the sine of 30, we know these, we know the mass, and we know the radius. And so we can solve for a v. No problem. So that is the first part of the question. Now, they're saying that they're detaching. So this took me a little while to pass. The way they phrased this question, but they're saying that someone cuts this off, and then they move the particle all the way to the end. So what does that mean? So our new situation is like so. So you have your axis, and you have this long string going down, and here's your B. And here's where it used to be. So blah, blah, blah. And we can work out what those lengths are, because we knew that at the beginning. So let's just mark them here. So this hypotenuse, in terms of so we can work it out, so the whole point is like sort of these triangles, they work with the angles, they work with the forces, but they also work with the actual lengths made, the actual sizes of these sides of the triangle. So we know one of the sides of the triangle, and we know an angle, so we can say that this is also equal to 0.6 over sine of 30 degrees, which is 6/5. So in the force diagram, this length sort of represented t, which was this business here. But in terms of actual sizes in space, it's 6/5. And we can do the same here with this 45-degree angle and that same radius there. And this is equal to 2 square root 3 over 5. So we know that the entire length, L, of the string now is 6 plus 2 square root 3 over 5. And now they're asking us for the tension in this new string. And they've given us omega. So this is omega. So just a quick review. This, when you have something moving in a rotational way, it has a number associated with it, omega, which is radians per second. And there are 2 pi radians in a revolution. So if something is doing 1 revolution per second, that means that omega is equal to 2 pi. Okay, so this is sometimes called f, or the frequency, and omega is called the angular frequency. But I mean, it's just pointlessly confusing. But f means like how many revolutions or how many cycles, like full cycles, has gone through. Omega refers exactly to radians, and omega is 2 pi f. Now v, the speed, is also called the instantaneous speed or the tangential speed, is kind of, if I just pause for a moment and consider the thing which is moving around in a circle, if I cut that string, so okay, this is a bad diagram, but so if I have something that's moving on a string from some central point, it's moving like that. If at some point I cut the string, the ball wouldn't have any force exerted on it to pull it in. The only reason it's moving in a circle is because it's being continually pulled in by this string. If I cut the string, it's just going to head off in a straight line. That's the whole idea. So rotational motion is actually a kind of acceleration, in that a force is being exerted on you, and you're accelerating, not in that you're getting faster, but that you're changing direction, because acceleration is a vector. It has magnitude and direction. Velocity is a vector, and it has magnitude and direction. I think that's actually what I meant to say. And so if you change the magnitude of a velocity, you've accelerated. We're all familiar with that. But it's also true that if you change the direction of the velocity, you've accelerated. If you turn a car, it's even if you're traveling at exactly the same speed, you still have to exert a force from the engine to turn the car. So you've accelerated. So the point is here, in order to go around in a circle, you have to have some force causing the acceleration, and that's the tension in the string. If you cut the string, that force is gone. The thing isn't going to suddenly curve around. It has no force to make it do that. It's just going to keep heading in a straight line. And that is what we mean by tangential velocity, because it'll head off at this tangent to the circle that it was moving on, right? So at that instant, whatever speed that is v. And it's related to omega by v is equal to r omega, as I said before. So we're given omega, and we're asked to calculate the tension now. So we again have this equation that T, or which is F, it's not actually, let's just look at the component in the horizontal direction. So we've got some tension T, and that's got some component here. Let's call this angle theta again, or alpha. It's a different angle now. So this is going to be T sine alpha, right? And we know that T sine alpha is the centripetal force, the one it's like the the tension in the string here when everything was horizontal. Centripetal force, which is equal to mv squared over r. But now we've got a different situation. So we have, well, actually, let me write that as, so if I plug in the v is equal to r omega, that gives me mr omega squared. And what is r? Well, so this was talking about t and t sine alpha as sides of a triangle in sort of force space, but let's look at spatial space. We know the hypotenuse, which is this length L, and we know this alpha, it's the same alpha. So therefore we know that this radius is going to be L sine alpha as well. So that's r. So that's all we need. So we get that T sine alpha is equal to m L sine alpha omega squared. The angles cancel, and then there you have it, ml omega squared. So, and we have all these things, so we just plug them in and work it out. Okay. This is another sort of balls on strings question, perennial favorite. So we have a particle attached to one end of a light elastic string. This is a vertical question. So we have some point A, and we have a string going down to some particle P, resting on this surface. And what forces are at play here? Well, we know that the people obviously have a weight, mg, and there therefore will be a reaction force, r, and there will be a tension in the string T. And those are all the forces that are acting at the moment. So we want the magnitude of the force exerted on P by the surface. So we've got to remember that R is always just equal to, if the thing isn't moving, if it's in equilibrium. So it's in equilibrium, therefore it can't be moving. If the forces were unbalanced, it would be moving either up into the air or burrowing to the ground. And we know it's not doing that, therefore all the forces must be balanced. So we know that the reaction force is always equal only to what is sort of exerted on the ground. So it just reacts to exactly what's exerted on the ground. And if there was no string here, that would just be the full weight of P. But you've got the string kind of helping. So that means that the reaction force is mg minus the tension in the string. So we have the mass and we have g. But what is the tension in the string? Well, that's our old friend, lambda over L times x. Lambda we're given, L we're given, and x we're kind of given because we're told that A is 0.8 meters above and that the natural length is 0.75, therefore x must be 0.05, the difference. Like, so it's been stretched just a little bit in order to do this. So that will give you the correct answer for the reaction force. Okay, so now we're in a completely different situation. I don't know where they're still referring to the same ball, but really it's completely different. So we still have the string. I guess it's not so different. But we're not caring about vertical motion at all anymore. Everything is horizontal. So we have this string with some tension in it and making this angle theta. I should change colors. I've been doing it in black and white for too long. Theta. And therefore this angle here is also theta. A. And again, we have mg acting downwards, and counteracting mg, we're going to have t cosine of theta, and we're told that p is leaving the surface at this moment. So it's no longer really exerting any force on the ground, and so there's no reaction force. So these are the only vertical forces at play. And it's just about to leave the surface. So these forces are balanced. It's not quite moving yet. So they're exactly balanced. T cosine theta is equal to mg. Well, why is this useful? Well, we know that t is lambda over L times x. And we know that that cosine of theta, so think of this triangle again. The cosine of theta is just going to be this, I'm going to call h, so the height of A, divided by L, the length of the string. So this is h over L is equal to mg. So x is equal to mg L squared over lambda h. So m we have, g we have, length, that's the natural length of the string, we have that. Lambda is the modulus of elasticity, we have that. H is just still the same height of A, 0.8 meters. So we have all these things, and so we get x, no problem. And now they want to find the speed. So this was question 2. And now we're on question 3, and we want to find the speed of P at that instance. So the speed of P is going to be whatever speed it was to begin with, but counteracted by this force that's acting against it from the restoring force of the strings, the tension of the string. So this is going to be a function of where you are, right? So we're talking about the horizontal component, which is acting like so, and that is counteracting the motion of the particle. So this is going to be t sine theta. But t is going to, t sine, the angle theta is changing as you move along, right? So when it's right at the beginning, theta is 0, there is no horizontal force. But as you move, theta grows, and so the horizontal force grows. So it's a function of the, oh, you know what? I've realized I've just looked at an old version of the previous question. I was a bit of a doofus, and I kind of messed it up. So I'm going to redo it. I'm sorry about that. I actually kept getting the wrong answer because I was forgetting a small point, and I've gotten it again. So from the top, let's do this super clearly. Here's our situation. So I'm going back to question 2, sub-question 2. So here's our situation. I'm drawing my triangle again. Here's our ball. Blah, blah, blah. So I have mg. That much is correct. I have t cosine theta. I have t acting there. And this is, oops, t sine theta. That's theta, that's theta. Okay, so again, the idea is that we sort of have these two versions of this triangle, theta. One where it's t there and mg here. So these are the forces acting on this thing, this like so. But we also have this one, which is h, and not. Oh my god! The point I'm making is that earlier when I talked about L, that was not correct. It was actually L plus x is the length of this hypotenuse in space. So previously I referred to it as L, which gave me the wrong answer. So let's talk again about how we're just about to leave the surface. So it's true that t cosine theta is equal to mg. So that's still true. The vertical forces are completely balanced. But now the cosine of theta, so this is theta, and this is L plus x. So the cosine of theta is actually h over L plus x. So this is t h over L plus x is equal to mg. So if we rearrange, you just take this onto this side and you divide everything and you get that x is equal to L over 1 minus lambda h over L mg. Because remember that t is equal to lambda over L x. And you get this expression, and this will actually give you the correct answer. So sorry about that. Worth going over yourself. And you'll find that it does give the correct answer. The other version did not. Okay. That's much better. So now we can look at question 3. And this is actually kind of less tricky in that there isn't a little thing like that for some reason I was blind to. So again, we have this instant where it's leaving the surface. So we have our x here. In fact, I'll just say this is equal to 0.074 meters. So we know that that's the distance that it's moved. So this is our x final, let us call it 0.074. And we have that our initial speed, like when it was over here, our initial speed was 3 meters per second. And our restoring force is minus kx. This is like, the elastic restoring force, the force that's acting on the particle to pull it back, which is minus lambda over L x. And you remember that the elastic potential energy is given by V is equal to 1/2 kx squared. So this is a conservation of energy question, which is why it's much easier. So conservation of energy. So at the beginning, we've got some kinetic energy, 1/2 mv0 squared. And we've also got some elastic potential energy, which is this stuff. So K is lambda over L, right? So we have plus lambda over 2L x0 squared. So that is the extension in the elastic string. So that's how much here the extension was 0.05, right? And now we have and now it's longer. So now it is this one. And that's when it was here at the beginning, there was only a bit of elastic potential energy and this potential energy that we gave it in the second part of the question. And this is now equal to no potential, more potential energy, but at some later time, V prime squared, plus lambda over 2L x prime squared. And we're trying to find this V prime squared. So we have M, we have V0, we have lambda, we have L, we have x0, which was 0.05, we have x prime, which is 0.074. And so we can solve for V prime, no problem. Okay, center of mass question. Question 6. So this one pretty much just relies on repeated application of this formula. M total times x center of mass is equal to the sum over I mi xi. So this means if I have an object made out of composite objects, the total mass times the coordinates of the, like the vector coordinates of the center of mass, is equal to the sum of their individual sort of, it's like a sum of the center of masses, but weighted by what mass they are. And this kind of works, works in reverse too. So if I've got some big object and bits cut out, I just register that as sort of negative mass, subtracting that mass. So the very first question is asking, so it's asking you separately to get the x and y coordinates of the of this center of mass of the composite object. I'm just going to do it in one. So do it as a vector, and then you can extract the center of the thing. So what is the total mass? Well, we know we're going to assume that this has unit density, right? So that means that, you know, every square meter is worth 1. Like, we're not going to worry about the actual kilograms because they will cancel anyway. So we're basically just talking about the total area. So the total area of a circle is pi r squared. So we've got pi, and then we have 1.2 squared minus 0.3 squared minus 0.4 squared. So this is 1.19 pi, and that's the mass of the whole shaded region. And now we're saying that 1.19 pi times the vector of the x center of mass is equal to, and again we're going to use these masses, pi times 1.2 squared times the center of mass of the full circle. If it was all there, well, that would just be at 0, right? So that's the 0 vector, so you don't need to worry about that. Minus pi 0.3 squared, and wherever the center of mass would be of A. Well, that we're told that OA is 0.5, minus 0.5 from the x-axis, and nowhere up and down from the y-axis. That's going to be minus 0.50. And for the last one, 0.4 squared. And this one is 0 on the x-axis and minus 0.7 on the y-axis. And this gives us an x of something like 0.038, 0.0941. And then this is obviously the distance from the y-axis, as in the x-coordinate is the distance from the y-axis. And it's just a little bit along there. And this one is the distance from the x-axis, so it's up a little. So it's somewhere there. The next question, calculate the angle that OA makes with the vertical when the object rests at equilibrium. So the point about this is to say, is to recognize that rest at equilibrium means that the center of mass is directly below the pivot, or whatever it is that's hanging from. So it's hanging from the axis, let's say. So our axis is through O. So what our thing will look like is going to be the center of mass sort of hanging below O. So here's O, and here's our center of mass. And it's hard, you just basically got to rotate it in your head. But so these were the original axes. I'm going to put them in a different color. This was the original x and y axis. Were they? Yeah. And that was sort of, yeah. So there's some sort of, actually it's easier to draw it here. So we're going to imagine that the new axis sort of goes through there. So it's pointing upwards. So this is up now if we rotate our screens, so that the center of mass is directly along the line and below O. So what they're asking is the angle that OA makes with the vertical. So OA is this one. So they're asking for this angle, which is the same as this angle. Well, what is this triangle? Here, this one. We want this angle, right? Well, this triangle, the angle, it's similar to a triangle which has the x-coordinate of the center of mass on this side and the y-coordinate of the center of mass on that side. You see that would be the same angle because it sort of goes to the center of mass. And so we can just say that the tangent of that angle is y of the center of mass over x center of mass, and that gives you the angle. Okay. Final question, I think. So this is one of the projectile questions. So we have a slightly complicated scenario. We have two projectiles, and one gets fired off, and then a little bit later another one gets fired off, probably not going in a straight line, probably going in some sort of arc, and at some point they collide. So what does it mean for things to collide? Well, it means that at some time they share the same coordinates. That they have the same position. So what we want is expressions for the, let's start with the x coordinates. So we're actually measuring time. Time equals 0 is when q starts being in motion. So p actually starts its motion at time t minus 1. The time minus 1. It's a little bit confusing. I think they did it the wrong way around, but whatever. So x of q, so let's first look at the x coordinate of q. Well, that's just going to be the velocity it had, cosine of 45 degrees. So that's it. When you're sent off at a velocity like this, the x coordinate of your velocity is obviously v cosine theta. And there is no force acting in the horizontal direction. So the x velocity is always going to be v cosine 45 degrees times time, sorry. So the velocity is always going to be that, the x velocity, and then to get the distance you've traveled, you times it by t. And for p, that's going to be v cosine of 60 degrees times t minus 1, t plus 1, sorry. Because when p is fired, time is equal to minus 1. So its distance is minus 1 plus 1, which is 0 traveled. Whereas for q, it's fired at time t is equal to 0, which is a second after that. It's 1 second after minus 1 second. So yeah, they've done it a little bit confusingly here, but this is correct. So this is equal to v over square root 2 t plus 1, and that's equal to v over square root 2 t. Wait, so this is not over square root 2, this is just over 2, that one there. So we know that these things have to be equal if the two things are colliding, so the x coordinates have to be the same. And this gives you t is equal to 2.414. If you did the wrong way around and did like t there and t minus 1 there, you would get something that was 1 second too late. And that would be because you were counting t from when p was fired, not from when q was fired. We're counting it from when q is fired, so it's 2.414 seconds. So now we want the value of v. And so for this, we have to look at the y coordinate. So we know that y of p is v sine of 60 degrees times t plus 1 minus 1/2 g t plus 1 squared, because there is a force acting in the y direction, there's gravity. And the same for yq, v sine of 45 degrees t minus 1/2 gt squared. And we know that these things have to be equal. And we know what time they're equal at. So if you plug in 2.414 for all these times and set them equal to each other, you will get the correct velocity. That's all you need to do. The last task is to calculate the vertical distance of P below its greatest height when P and Q collide. So what does this mean? Well, best draw a diagram. Okay, I don't know what that's about. So we have some trajectory followed by P, and it reaches some maximum height, h, and at some point here it collides with Q, and it hasn't fallen to the ground yet, or fallen back to its starting place. So let's call that h prime. Well, what I want to know first is the maximum height. So this is done by, called HM for H max. This is done by conservation of energy. So we know that at the beginning, it's only got kinetic energy, 1/2 mv squared. And this is going to be equal to mg H max. And for this, from this we can get H max. And then we can just look at our previous expression for what the y coordinate is at this point. So we know the time of the collision. So this happens at t is equal to 2.414. So therefore we can say, what is the y position of particle P at time of collision? Well, we just take this expression and we plug in the time of collision, and we'll get something involving v. And then we've already found out v. So sorry, we will just get this h prime. And then we know that the distance, vertical distance of P below its greatest height when P and Q collide, is h max minus h prime. I hope that's clear. Sorry if I got a bit lost. I'm a little bit ill, so maybe that's interfered with the way I've expressed this, but I hope that was clear. And please do let me know online if you have any questions about these or you want me to go over something in more detail. I'm really happy to help. Thanks very much.